Okay, welcome. I'm glad you all showed up for the Philly Bike Expo. It's my first time here. I've been to NABS, I've been to Interbike, I've been to a lot of other regional shows and stuff like that. My first time at Philly Bike Expo, so I'm really excited about that. And I've always heard lots of good things. I'm going to go pretty quick here. And if you want to come, like I said to some other people, we're going to have some pizza down the street. It's a block away. There's the address. If I don't have time for questions, if you have something that's burning and you want to ask it, go there and I'll try to answer your question in long form directly to you or whatnot. What am I doing here? Let me just get a quick show of hands. Who wants to shred it, or who wants me to be in the engineering weeds? You know, who wants like pretty pictures and, you know, roost?
I want somewhere in the middle.
You want somewhere in the middle? No, you got to pick a side, bro. You got to pick a side. All right, I'm going to go into the weeds. How's that? That's what I want to do. That's me being my true self, okay? Okay, so we're going to talk about this stuff. Here we go. Okay, all the math and science in the world won't tell you what will work at the racetrack, but it will tell you what won't. We just talked about that. We got a big problem in cycling, okay? It's largely a marketing problem. Right? No one really succeeds because they're doing better engineering largely, unless it's saving them money in production somehow or their shipping problems. It's a marketing-driven business. Like I like to say, it's 95% marketing, 5% manufacturing, the rest is engineering. We have a problem in that most of what people have learned or what they know about bicycles has come from the marketing and sales department. All those magazine articles that you've read or do read or whatever, talking about bike geometry or wheels or whatever, they were designed to do one thing: maximize the value of the advertiser's dollar. That's how magazines earn their money. Their goal is to sell shit. They don't care if you learn anything. Or actually, one thing they do want you to learn is to buy their advertiser's product. So generally, what you're reading when you read a technical article in a magazine is ad copy supplied by the marketing department of the manufacturer. That is how it works. And it's very difficult to have a real honest discussion that isn't geared towards selling stuff. You know, the early builders did their best, but there was a lot of clouded understanding of what was really happening. Is what we know now the true, correct story? Probably not. We've got a ways to go, but we've made a huge amount of progress, especially in the last 10 years. There's something I like to talk about, especially with bike sales, is the McNamara fallacy. Anyone know what the McNamara fallacy is prior to this? It's very important. If you can't measure what's important, make important what you can measure. It comes from the Vietnam era when Robert McNamara was the Secretary of Defense. He was a bean counter, and it led to some huge problems. In the bicycle industry, generally, we use weight. Weight, any novice rider working in your sales desk at your bike store or whatever like that can sell a product as being better than the other and worth the added money because they're trying to get the money out of your pocket based on weight. And that's what a lot of the industry is built around, in that it's very difficult for that person to hire a person that has the expertise, knowledge, and understanding of what is a better bicycle product or better bicycle fit for somebody by using real measures of what makes a bike better or getting into the weeds on it. But if they put it on a scale, anybody can say that's better. And that's largely how it's been constructed. Now, there's some exceptions, and these days I think in the road market they're starting to do that with pretend aerodynamic tests and things like that. But the thing is, it's largely been weight for a long time. And the thing is, that's not always true. Weight's a parameter, but it's just one of them. And in terms of the very important ones for the cyclist that's using the bike, it's like down near 8 or 9, or maybe even lower in terms of priority and importance. So we need to start thinking about it for frame builders or designers of parts in a better way. So let me just talk here about meaning, and I think this is really important if you're going to play this game, because you're not going to get rich being in the bicycle biz or working with bikes. It's a game of passion. And for me, what got me here, I was a skateboarder in Boston. I was a Maximus guy. Kenny Deutsch was one of our mentors back then. If you know ancient history of Boston, this was probably a big thing. Then I was a bike messenger. I work at Fat City Cycles. I become a machinist. I moved to Durango right in the middle of all that shit. Work as a motorcycle mechanic, and I come here and come to California, work as super bikes, blah, blah, blah. A bunch of my friends start a fancy company. I do my stuff with skateboard stuff. I start designing parts. I get into real motorcycle tuning and things. I think it's important if you're in these worlds and trying to churn around making bikes or thinking about bikes in grander levels, what got you here? What's your path and what's motivating you to spend all this money? We talked earlier with you about your huge motivator. It's a very tall fellow here. I can guarantee almost nothing available is gonna fit him on a retail level. He needs a custom built bike. The only custom builders that I know that are specifically marketing to tall people are probably not building very good bikes, and he wants a good bike. So this guy here, I can, right off the bat, very simple. You got a damn good reason to build bikes. What do you guys got? Why are you gonna do it? It's hard work. It's very expensive. And I think, I've got a proven thing of this is my bag. I call it tilt steer vehicles, bicycles, motorcycles, and skateboards. The rider is a mechanical part of the system, and they play a huge role in how the dynamics work. That's my bag. In with that, we're going to talk about authenticity, truth, values, and status. Status is huge for us, and it's a big topic in a lot of the thinky stuff that's happening these days. And it's like, what is our motivation for doing stuff, especially in the Instagram world? And I know I'm going to get to engineering shit soon, but I think this is important because you don't want to just get into this stuff willy-nilly. It's like, you're trying to boost your status somehow. And don't get around it, sounds shallow. That's the game, right? We're boosting our status within society somehow. And there's shallow and terrible ways of boosting status, and there's really meaningful and important ways of boosting your status. If you're hunter-gatherer and you're the one bringing home the big kill, that's a big boost in status, and it's valuable to everybody. Versus you can take selfies at the baller bar. It's not very valuable to anybody. Whatever status you're including isn't very important. So status can be good, it can be bad. And also it's like, are you just filling in time? Are you just wasting time, spinning pedals? Are you doing something that's important and meaningful to you? Because like I said, it's very expensive, time consuming. It hurts to work long hours, especially after you've already done a shift at your day job to do this stuff. And also, when we talk about like intellectual honesty about what you're doing, because we can fool ourselves very easily, are you willing to lose status by doing something that you truly believe in? It can be very costly to look like a fool in front of other people, even when you're right. Because the popular consensus is what defines who a fool is, not factually being correct or improving something. If it looks silly to somebody because they know what it's always looked like, and I've heard plenty of this, in terms of, or it's going to reduce your status in some ways. And it's like, can you go through a momentary dip in your status, everybody thinks you're an idiot, until 5 years later, wow, we knew that all along, even though they didn't. We all know that happens, right? So thinking about this stuff is very important before making these investments. And they're massive investments because they're your time largely. And your time is the one thing you have. Everything else is make pretend. Your time is a huge investment. And when you get into this stuff, and we see a few people here who have invested massive parts of their lives into this. So that's a massive investment. Okay, let's talk about engineering now that we know why we're doing it. But really, this is why we're doing it. What's the problem we're going to be solving? So, I work at a university. I'm not in the engineering department, but I interact with engineering students all the time, and a lot of them, They don't seem to understand what engineering is, even if they've gone through the whole program and they've got a degree and maybe they've even worked in it. Engineers solve problems. Nobody wants to hire an engineer that can't solve a problem or finds a more expensive way to solve a problem or can solve a problem but it breaks down all the time. That's not very valuable. We want to solve problems well. We want to solve them efficiently and cheaply. I can let you folks read this stuff, but you know, we have lots of ways of figuring out how well we're solving a problem. Necessity, of course, being the mother of invention. You know, that's an old Plato quote, but it's truly important. If you don't need it, why are you inventing it? You know, when people say, I want to be an inventor, it's like, well, you've already failed. Because invention requires a necessity. And if you haven't got a necessity, you certainly aren't going to invent anything of value. Because, well, if you don't need it, and obviously nobody else needs it, then it's just folly of some sort. So we really want to define things within a problem. You've got a problem. Bikes don't fit. What else do you might have a problem. Bikes are too big, and they don't fit you either. You know, so that's a very good reason, but other people might have a very nuanced reason where they might be more into the sculptural aspects, and their problem is they need a sculpture. Well, if that's the case, be honest. Don't claim to be a high-performance builder and that your bikes are race bikes, when really what you're looking for is a canvas. And that's fine if that's what it is. There's lots of builders that the bike is a canvas. And it's like, good for them, have a good time. Just don't claim to be a race bike, because that ain't what it is, right? Something cool that when I talk about engineering and try to explain like different modes of engineering, I'll talk about the AR-15 M4 platform. This is firearms stuff, but within engineering, like it's a classic example. The AR-15 versus the AK-47 in terms of a classic example of engineering where, you know, the AK-47 is a very cheap to make firearm. It's very simple to service. It never breaks. Children can use it, and that's a very important thing if you have child soldiers. You can sell them all around the world and everything like that. They're really great, but they're heavy and inaccurate. Okay? Well, you can solve the problem the other way with the AR-15. Well, that's great. You made a much lighter and more accurate gun, but it requires a lot more service. It's very expensive to make, relying on some very expensive tools and processes. And the soldier needs to be very well educated in terms of how to maintain it, and it requires a lot of steps and everything like that. So these are very different ways of going about solving a problem. They're both excellent platforms, but the way they go about solving the problem is different. And it depends on how you're trying to do it. You might be very interested in very crude caveman solutions that you can bang around and they just never break, but they're not going to be very light or feel good or anything like that. But they survive they survive the apocalypse. That's it. You know, that kind of bike. And that might be your bag. That's cool. That's a good way to solve a problem as long as you're very well defining the problem very well. One thing that just recently occurred to me, and I added to that, which I think makes a good example, is a Sturmgewehr 44. And if anyone knows firearms, that's one of the late 1944 Nazi firearms that it was essentially the first assault rifle that the Nazis rolled out. They brought into their SS troops and stuff like that. It was about walking fire and things like that. But the thing is that what's interesting about the Sturmgewehr and how it fits within this context, and I say this because it's a very good way of encapsulating this stuff, is Sturmgewehr wasn't a very good gun. You know, it had problems. And if you were to use it nowadays, it would be just a terrible choice. But what it was it was the first. It redefined a class. It changed the rules. And in some ways with engineering, that's something you're going to want to do. And that's so different because it's one thing for these guys to be trying to solve a problem going down their different paths. But the thing is, that's within a context that's been predefined. You know? What if this context has never been defined before? Well, that puts you into the Sturmgewehr crowd, where you have to invent something from thin air, largely. And that's a very exciting and interesting way of doing engineering, where nobody's been here before, or nobody's really gone down this road. Like, think about the person that invented the bicycle, you know? hey, everybody's working with wheelbarrows and I just added a second wheel. I'm killing it, you know? But everyone's looking at you like, I don't know, dude, it kind of breaks down more, you know, and you're just like, sorry, you know? Anyway, I'm just trying to say, keep your mind open to like these are good classical examples within engineering that define just different ways of thinking what your path is going to be and how you're going to solve a problem. Here's an example of an interesting problem. In this example, it's post-mount brake caliper mounting, something I dealt with a bunch a few years ago. If anybody here well-versed in brake caliper methodology and things like that, it's an absolute train wreck. Oh, it's horrific. And the horrific part of it is I think Shimano, who largely defined this system, their documentation department and their engineering department, I don't think talk to each other. And the person who defined the standard didn't seem to know how the system was supposed to function. So we ended up with this total cluster. And also this is, I mean, especially with this system, it started with Manitou with their first fork mount, and then Shimano basically took it over, and you got a bunch of things going on there. Well, I redefined that, and I redefined it in a way that makes sense methodologically. It produces accuracy and it can be extended in any way. You know, what is the problem I'm trying to solve? This system don't make sense. You know, I need it to make sense. That's the context that I like to work in. So I redefined that, and the system still works. It'll work with any system that's going on right now. And what you'll notice here, it's changed from the Shimano system. Shimano defines a 57-degree angle if you were to systematize it. This is a 60-degree system that SRAM stays truer to. I think currently, paying attention to the SRAM specification makes much more sense for anybody engineering stuff around the system than the Shimano stuff. But if you take apart Shimano calipers and look at the angle that they're functioning at, you'll see that they're probably functioning at about a 60-degree angle anyway. So the reality is this system works pretty darn good. And if you see, these spacing here is 10 millimeters. Well, 10 millimeters of radius corresponds to 20 millimeters in the diameter, which is the steps that we're working up. So we've got a true system. Anybody know motorsports with radial mount calipers? I mean, that's in a way what I'm looking for on a bicycle, but because of the space and mass that a true radial mount caliper system would do, we can't really use that, but we can at least base our system intelligently. So that's sort of what I was harking to when I developed this. Also, if anybody knows my work, I've done a lot of work with the handlebar system, and that's stuff what we're probably going to see from major manufacturers in the next few years in the performance end of the flat bar market, where if you look at, let's say, the handlebar end position here of my system, which is green, and the traditional, say, 30 millimeter stem is shaded out here, the end of the handlebar is approximately the same with a 9-degree bend here. But if you look, I'm allowed 36 millimeters more shift forward where my head tube can move. And if you know about modern bike design, we'll talk a little bit about that maybe, we're moving the front wheel so much more forward that traditional handlebars and stems don't function. We're building bikes largely around the stem and not the wheel. And the thing is, the stem doesn't mean anything. The wheel means everything. The hand grips mean everything. Why are we defining the front end by something that's meaningless that happens in between? So I'm just trying to show, I had a problem. My wheel wasn't where I wanted to go. I had to decouple my front wheel from my stem so I could have my grips where I want them, my wheel where I want them. That's what mattered, and the stem sort of morphed into this, and that solved the problem. And that's why I went down this road. And you don't do this stuff willingly. I got a lot of flack about this. This is like that whole thing of like, are you willing to lose status? And it's like, how many people are laughing at Pete's stupid looking stem thing here? Well, don't worry. I give them about 5 years, and they'll tell me that they knew all along, you know? Here's another solution in terms of the bent seat tube stuff. I did a lot of work to define how we bend seat tubes within mountain bikes and all-road bikes, essentially anything where you're looking for clearance back here. You know, we look at our rim, our outside of our tire diameter, we look at a little mud clearance. Essentially, the edge of our yoke or bridge and the seat tube and the chainstay yoker bridge should essentially be tangent to that clearance line at the 3 points. But we're looking for dropper post clearance, so we want to maximize the straight section here in the current vernacular in terms of how we attach our saddle to the bike. So we need to have this room. Later that will change because this is a dying system, and we'll be going to a linkage system, but that's, for now, this is where we're at. And so we put a really tight bend right at the bottom. You know, for a while I was doing a very fancy and expensive bend. Rody knows all about bending tubes. And a 3-inch bend on a 1 3/8 tube is very challenging and expensive. And now with 3D printing, like I discussed, now I can do a 0 center line bend for that tube and buy myself an additional 20 millimeters of seat tube. Currently, when we're looking at dropper post stroke, which takes up most of this room, or allows for most of this room, we're looking for mountain bikes to be, for my size rider, average 5'10", to be about 250 millimeters. And surprisingly, for all-rotor gravel bikes, we're probably looking at about the same. Once people get into higher speed, off-camber and flat corners, you're going to want to be steering your gravel bike more like a motorcycle, where you're shifting your body, and that you need that translation room. So we'll start to see gravel stuff really start to climb. Okay, risks and failures. So you're engineering, you're solving a problem, you think you're really cool, and you've got this great solution, and you start implementing it. Well, you've got risks and you've got failures. You know, the big thing here for more people than not, if your mistake kills somebody else, you're going to hell. I worked in motorsport and everything like that. And in motorsport, you've got a team of about between 5 and say 20 people working to make sure one person is the fastest person of the day. And to do that, you put them in a very dangerous situation that relies on everything working perfect. Well, I shouldn't say that. That relies on everything not failing so that they survive, at assuming the worst doesn't happen. But the thing is that if you make something and it fails and somebody dies, you're gonna burn. I mean, that's just how it works. So engineers start getting really uptight about being right or wrong, right? Because somebody's life could be on the line because of some decision that you just thought was whatever, we'll just do this. And it's like, no, it really matters. Someone could die. And that's important. So, you know, there's small stakes and low stakes poker. If you're playing, or small stakes and large stakes poker, if you're playing large stakes poker, you better be checking every little thing and making sure. Yes?
Sometimes the executives make that decision. You know, like Boeing's 737 MAX.
Sure.
That was executives, not engineers.
Oh, sure, we could talk about Challenger disasters and everything like that, but the thing is, we're trying to talk about what are you doing as a frame builder within this context. I'd love to go down that road, but I just don't have the time today. But yes, if you're working around a system where other people are making the decision, I mentioned the Challenger disaster. You know, Boeing's got a problem right now, but you know, if you've ever heard the story, it's very incredible, and a learning lesson is that the flight, I think it's flight manager for the Challenger, if you know the Challenger that blew up, the flight manager made the call that morning not to launch. The flight manager said there was a problem, it was too cold, we were having problems with seals, and don't launch. He was overridden by the upper people. His authority to make or call the launch was overridden by higher ups, and they said, you're going to make the launch because we got a teacher on board and this is good PR, right? Well, that thing blew up. Guess who's not going to hell? That guy that tried to stop that flight because he knew it was wrong, and he was willing to lose lots of status to make that call, and they launched anyway. And I mean, it's a terrible thing to think, but good for him that he tried. But those other people that overrode him are going to burn, because this is important shit. And I make it sound seriously, but I take it seriously, and I'll show you why. That's how a bicycle's supposed to fail, okay? We've got a butt that ends about there. Front end of this was completely overwhelmed, slamming straight into a curb in San Francisco, and folded up the front end. Well, I mean, yeah, I smashed my face up against a curb, but that's no fault of the engineering. I shouldn't have ridden straight into a curb with my hands off the handlebars. That's on me. But this bike failed correctly. That's what we want to see. It's buckling right at the butts where the tubes start changing their wall thickness. The tube didn't fail catastrophically. It didn't fail. The welds all held. That's exactly what we like to see in a worst case scenario. That means you did your job. This isn't, okay? This happened to me last year. I do a lot of work with my handlebars, like I said. This is on my clunker. And I had a catastrophic failure of not just my handlebar, but my wheel. If you look, this wheel is folded. And I've talked with WTB, and they've never seen a failure like that. Nobody I know has seen a failure quite like that in the front wheel. And we've seen broken handlebars. And sadly, nobody saw this happen. There was no videotape, so we don't know which went first. Problem is, one of my parts failed. I broke my collarbone and had to get surgery and got bonked pretty good. So that's pretty terrible. This is a filament wound carbon tube. After this, I went into my postmortem and looked at everything and talked with a lot of composites engineers. Soon changed my stuff to a pre-preg roll wrap and type of filament that's within the tube to try to, we don't know exactly how it failed. A lot of fancy engineers said, well, I think you just got unlucky. But I'm not looking for luck. I'm looking for ensuring that this doesn't happen again. So I completely removed all this carbon from all my handlebars that I'd ever made and replaced them with a different type of handlebar that has done well so far. Oh, so there are high stakes when we're playing this game. It's something to be taken seriously. One thing that we want to do when we're engineering is we want to talk to experts. There's a lot of people, there's a bunch over in that corner, that are experts and they know exactly what they're talking about. They've done this before, or they've seen the failures, or they've seen other people do it wrong. They have a lot of experience. One of the things that I think is really kind of problematic in the modern world, and I've written a very controversial blog post about it, is trying to evaluate who's an expert. You know, in this world where everybody has a voice. Well, 99% of people definitely should not have a voice. A lot of people are not experts. There's a real difference between what makes somebody an expert and what doesn't. And this world where anybody can post a comment and say, I know what I'm talking about. Well, show me your portfolio. Show me your experience. Where have you been? What have you done? I need to evaluate you before I'm going to listen to you. I mean, unless, of course, the comment stands on its own, which you should evaluate yourself also. But the thing is that, you know, I look for people who are experts and I ask them questions. I talk to them because I can learn from them. I don't want to do it all. I'm not a one-man army. I'm not going to do it all on my own. And there's thousands and thousands of years of experience up in that convention hall of people that have done something that you might be trying to do. Talk to them. Cold call them. Some of the best things in my life have happened just calling somebody cold out of the blue. These are some books. These are probably the top books, I'd say, in terms of this world. Of course, everybody has a copy of Sharp, but of course, you have to have a copy of Full. If you like math, Casalter is really good. Bradley is very practical, and this motorcycle design technology, it's very good, clear, like Sesame Street level diagrams and some math and things like that. I think it's worth having something in the bathroom, you know, that kind of thing. But these are very good books to have on your bookshelf if you're interested in this kind of stuff. Here's a picture. You guys know Sandy Cosman from back in the day? Yeah, Sandy's in rough shape right now. But I went to his shop in 2008. I cold called him. I said, hey, Sandy, you're the guy. I'm all about motorcycles. I want to go check out your shop and talk to you. I spent the whole day with Sandy Cosman and talked about, you know, life, liberty, and the pursuit of happiness and all that shit. Saw some crazy shit I'd never seen before. You know, the first carbon fiber motorcycle chassis I'd ever seen was in his shop. before I even saw it in a magazine. He's pretty crazy, total legend in California for motorcycle drag racing. So I was there, I talked to the guy. That was 12 years ago, or 14 years ago, Okay, testing. Showed the stuff earlier. My favorite Nazi, right here. One good test launch is worth 1,000 expert opinions. Who said that? You said, it's right there. Werner von Braun, right? So he was a pretty emphatic Nazi, and we grabbed him, brought him here, and he designed our entire space program, and basically got to live his dream for the rest of his life, designing the greatest rocket ships, the Saturn V and many others that the world's ever seen. So, but the thing is, it's like we can talk all day. Everybody's full of theories and opinions, and they'll tell you what they think or whatnot. If you've actually tested it, if you've tried it, that's more important than all that shit, is actually getting out there and really doing it and finding out. Because we can find out. You just have to do the hard work. Well, get off your ass and do the hard work, because that's what's really important. Said all the math and science, never waste a prototype, all that sort of stuff. We have a lot of ways of looking at stuff in terms of testing things. I think two things I would say coming out of this is learn about bracketing. I do a lot of testing of my bikes, and I'm trying to take a holistic view of my bikes, not just the frame, but parts and how the parts interplay. Bracketing is you take your hardest condition of some sort, and you take your lowest condition, test it at each end, see how well it performed in those ends, and kind of find where it fits in that setup, and then you can move the brackets around and everything like that. Like last weekend before leaving, it was a rain ride, riding some double black diamond single track in Marin, soaking wet trails and everything like that. I'm on an all-road bike. My all-road bike's a little different than other people's all-road bikes, but completely overwhelmed the flat mount calipers. Now, granted, I'm using modern Force flat mount with RSC levers, which is about the best flat mount setup I've experienced. If you're looking for the hot shit for flat mounts, I've tried pretty much every configuration. But those conditions completely overwhelm the system. I'm going to have to move to a post-mount environment if I plan to use that bike in wet conditions in the winter on double black diamond trails. And it's like I passed the bracket point where it had been the brakes weren't great. It's an all-road bike. It's not intended to be a DH bike. But the thing is, I expect it to function on the hardest trails I know. And once trails got soaking wet, because we've been in a drought, so I wasn't privy to a lot of good wet testing last year or something like that. And I've changed my brakes since then. But the thing is that I'm finally in a test condition where I can find, okay, I've completely overwhelmed the system. I need to change something if it's expected to work. And you want to find those places. Testing a bike isn't going out for a ride. Testing a bike is finding conditions where it starts failing or it truly excels. That's testing. Just I went for a bike ride to the coffee shop is not a test. If you can't make a bike that does that, just don't, right? And also a really good important thing for testing and to understand is your racer buddy isn't a test rider. What it takes to perform well as a racer is not the same thing that it takes to be a test rider. In motorcycling and motorsports, we don't use racers as test riders. We use test riders as test riders because they have to have an understanding enough and a communication level enough to be able to relay to the engineer or the designer what's going right, what's going wrong, what might be the possible problems. Now, you might have a Valentino Rossi that's got 20 years racing at the top with the best people, and he might be able to do a pretty good job with that. But generally, in the world of athletics, which is what, bicycling is, we have the myth of the dumb jock in society. And it's like going to ask the captain of the football team what the answer to the math problem is. And it's like, his job is not to work out the math. His problem is to hit a bullseye, And it's like, he doesn't have to know why or how. He just has to have faster reflexes, more strength, and all that stuff. And it's like, I've known plenty of bike racers or whatever that I've given test rides, let to have test rides on my bike, and I have gotten less than 5-word responses for what went down on the ride. So not looking at racers as the testers, but looking at somebody that might have a very deeper understanding. They ride well enough where they can take it to an environment that the bike is adequately tested, but they don't have to win the EWS. But what they have to do is be able to communicate to you. That's one of the big problems I'm having. I'm going to be 52 soon. I'm getting too old for this shit. And while when I was younger, I used to be able to test my bikes to the limits, that's starting to become something I can't do. And I'm trying to find test riders, and I can't. I can't seem to communicate or find people, the younger generation, that are just very interested in doing much besides taking selfies. And it's a problem. And it's like, you think this stuff would be cool for kids, but they're not. And it's like, I don't know what to do. So I'm in a pickle myself, because what I could do myself, I can't do now. Okay, also in testing, you have laboratory testing, destructive and virtual testing, where you can break shit and build test rigs and all sorts of stuff like that. Or you can virtually do it with some FEA, some CFD and things like that, and do aerodynamic testing in your computer, do FEA. There's places for this, there's value in it. It's not all it's cracked up to be. People like to sell product, talk about that. But you have testing protocol and specifications as defined by the ISO in the United States, and various measures that you want to go through. And you have testing service labs. There's 2 spots in the United States that I know of. There might be more. I'd love to hear about them. That can actually go through the EN testing on various product that you might make if you're looking to sell it and be insured and protect yourself in a lawsuit. That's another thing about all this stuff. If you're writing it down and doing the calculations, doing the testing, if the worst happens and if somebody dies because of your shit and you're in a lawsuit, you might need to prove something that if you can't prove it, you might get you in a lot of trouble. Also, if you have IP, so the documentation and the engineering notebook that you might keep is very important for several reasons. So we like documentation. It's really good stuff. But yes, there's a way to test. It's been defined. And know the testing protocol. It's worth reading, because if you like to play with FEA, if you're a young person or student and you're like, oh, FEA is the way I can do this stuff all in the computer. It's like, well, these testing protocols could at least define some parameters that you'd be designing around. Have someone else do some of the hard work for you, because getting those parameters for FEA is the real devil in that detail. Okay, this is somebody at a World Cup recently this year. This is a terrible test rider. How do I know? They don't know what a fender is. Okay? They have lost all visual input into their processor because they're not using a fender. That is a very slow way to ride a bike. Now, it might be very trendy to not have a fender, but the thing is, if this is what your face looks like, you're not making very good decisions. Because if you can't see and you can't clearly know how things are coming up ahead, you're probably not going to be able to evaluate products very well. Drawing and data. I'm really big on drawing. I love drawing. Just a couple things. This is an important quote from writer. It's lost to time. I'm not the world's best writer, but I'm one hell of a rewriter. Your first draft sucks, always. Your 20th draft still sucks. You still got a lot way to go. You'll probably get there at about 40. And what's nice about the computers is we can do iteration after iteration and prototype after prototype in a virtual environment. And it doesn't cost us anything but our time. And we learn things in those environments. So go through lots of revisions and think about what you can change before you actually spend money on materials or expensive processes that you actually regret later when you actually do the drawing. Design for manufacturing. We have a lot of manufacturing techniques, and you really want to be designing or drawing that exploits the one you're going to be using, or how it is more efficient or economical to make things. That's very important. One thing I like to do on my digital files is save my designs with a date in the title, because it's very difficult to determine otherwise, because you might open a file and you have different dates within the, I guess I'd call it an EXIF, but the file data. But if you have it in the file name, you know what date that file was. And I like to go year, month, day, file name. I find that works very well because at the very least when I alphabetize it, it does put it in chronological order. And save waypoints. This is something I got in the habit of doing back in the Boolean AutoCAD days when you'd have to save a waypoint, go off on an adventure. If it didn't work out, you'd have to go back to that waypoint because you were basically screwed. We don't really do that anymore, but it's a good habit. Now, this is a frame building crowd. We're all about bikes. You know, I'm into solid modeling and SolidWorks and all that shit, and we get lost in the weeds and FEA and CFD and everything like that. If you're into bikes, the best money you can spend is on BikeCAD. Absolutely, bar none. If you aren't using BikeCAD and you're looking at performance use of bikes, racing bikes, setting up bikes, or making bikes, you gotta have a copy. Brent works so hard on this and he improves it all the time, and it's an incredible product. And I think if you talk to any of the frame builders that are up there and they say, number one, BikeCAD, always, it's the best. And I use BikeCAD all the time. I use it for my 2D fitting and profiling, and I do my roughs kind of in BikeCAD before I get into the 3D environment. It's a nice quick way to do it. And also, if you aren't used to designing bicycles or understand the terminology or methodology that we typically use, even some fit methodologies that are in there, that you can learn the terminology we use. Like if I say the word front center today and you're like, what the fuck is he talking about? You go into BikeCAD and you go, oh, there's front center, and you click it and the dimension pops up and you go, oh, that's the front center. You know, and all these terms of art that we have or ways of doing things or things, dimensions some people think are important, you'll find in there. He has pretty much every conceivable one. And whatever system you like to use, it'll probably be there. And it's a really great way to learn about this language that we speak, but also understand what you're doing. For very complex stuff, like right now we're talking about 3D printing, stuff like that. That's when you need to be in a 3D modeling environment. And that's, you know, you don't need to do that for frame building, but you do need to do it if you're going to be having parts machined or printed or anything like that. That's really the go-to stuff. And we have several platforms that we can go to. You know, RattleCAD does exist. That is out there. I will mention. I'm not trying to be a shill here on BikeCAD, but I do use it, and I think it's great. But there's several programs. SolidWorks, Fusion 360. SolidWorks is great. That's pretty much what all your machine shops will probably be using. That's very popular. Fusion 360's really gotten a boost with the maker crowd. And Autodesk really kind of changed the business model of solid modeling with Fusion 360, and it's really good if you have a mixed CAM design and CAM and drawing department. Camming and designing process that you need within your stuff. Fusion 360s is pretty good, but each of these programs have various drawbacks. There's Onshape, there's FreeCAD, which is, BikeCAD has added an export for 3D right now, which is pretty cool. I haven't used it, but people that like FreeCAD are good. You know, you want to learn about construction geometries and equations. All this stuff comes up. I don't need to read this to you, but also do the math. Math is so important. I love the math. Like, you know, we can get into all these modeling environments and quick sketch and all this sort of stuff like that. The math is real, and once you have the math, you can apply it to anything. Here's a bicycle. Now, I was going to ask at the beginning of this, can you draw a bicycle with 3 straight lines? Well, of course you can, because a bicycle is the rear wheel trail, the steering axis, and the mechanical trail, and how they contact the ground via the contact patch. That is mechanically how the bike works. If anybody's still using ground trail, stop. It doesn't mean anything. It's a ghost. We don't use ground trail, we use mechanical trail, because it actually is the length of the lever arm that this system is functioning with using the friction of the contact patch. And if we look at our center of mass here, where we sit, we form a triangle between those 2 contact points. Now, someone was asking me earlier about increasing rear center to front center ratios and things like that. And I said, how often do you ride your bike backwards? You know, because the thing is that this, in a way, this triangle is the stability of the bike, depending on which direction you're looking at it, and depending on which, say we're going up a hill or down a hill, this triangle will change. Granted, we will this center of mass will move somewhat. And this point here is based on some experimental data of mine. So that would be essentially me on my clunker. That's my center of mass. But the thing is, that stability right here going in the front is largely our forward. When we talk about long front ends, when we talk about front center, really what we're trying to do is change the attitude of this line, or this angle from the center of mass to where the tire contacts the ground. That's vitally important to, forward stability on a mountain bike, especially in rough terrain. Anything that goes in the dirt is really nice. I say gravel bikes are also really advantaged by the up and down movement and freedom that's afforded by moving the front wheel forward. But this is the fundamental line drawing of the bicycle and how it works. And if you look at these straight lines and think about how a bike feels while you're flopping around, that's it right there. One thing that I didn't draw here, because I think it's kind of later down the process, is this vertical dimension here, we'd call flop. That's the potential of that system. When we talk about the potential energy or the displacement of the mass. So if you let go of your handlebars, if we didn't have this friction created by the contact patch, that front end would flop right to the ground. Well, that distance, that potential that we have there, we call flop. And I've found that more than trail, the length of the lever arm here, the mechanical trail, flop is becoming a bigger factor in terms of how we're drawing and designing our bikes. And I would say, rather than, we're pretty much fine with trail. We're in the ballpark. It doesn't matter at this point. Start thinking about flop. It's really important. Here's the rest of the bike. So I added, this is a template of basically the dimensions I'm going to use when drawing the bike. Now, it might look like there's a lot here, but there's a lot that aren't here. Most importantly, you don't see any stacker reach numbers here. You don't see any effective top tube length here. You don't see any actual top tube length here. That's because those numbers don't mean anything. They don't do anything in the design. And that's not what I'm looking at. I'm trying to understand what kind of cockpit fit up do I have. I actually, in this, have some of my handlebar dimensions because I have to fabricate and customize my handlebars. So I want to know a little bit more about that detail there because I can't buy off-the-shelf product. But all these dimensions actually relate to something that's mechanically important within the system. There's not like ghost values like ground trail or effective top tube length that don't mean a thing. They don't add value to your understanding of the bike compared to the front center. This is the bike I'll be building later this winter. This is going to be a shorter travel. It's a 150 fork mountain bike. Most of my mountain bikes recently have been 180 forked mountain bikes. But, and you can see some of this later dimensioning here that we just added. I was talking with Brent a bunch before 17.5 came out about how to get this seat tube stuff really detailed right so that it's meaningful and important for frame builders. Now, in that, if we look back here, I was talking about this cockpit information where, the two things have to happen. We need to have a dynamic chassis that functions in an environment with that center of mass there that we talked about here. That has to happen. That's the bike going down the road or down the trail. But we need to get the person on the bike, so where the saddle is and where the handlebars are in relationship to the pedals, which I need to have a circle there where our pedals are. That's how we contact the bike, the touch points, right? Those are important for how we interface with the machine, right? So one thing that I've seen a great many frame builders do is completely ghost out that part of the bike. They start talking about stack and reach. They start talking about top tube length. But what they're not talking about is really fitting the rider, fitting the frame to the rider in a way that is special for them and everything. And a lot of that comes out of a misunderstanding and not having gone down the exploration of how the stem and handlebar area affects the geometry of the bike. And you can see here just some rough measurements. This is mostly 9-degree handlebars and how much displacement or vertical, between sitting on the countertop versus sitting on a bike. I found personally that for my general size riders, I'm looking for a 20-degree from horizon up sweep or sweep angle here. You can approximate that by pointing at your center of mass. Your center of mass you can approximate by your belly button. You want to know where most of the mass is. It's about right there. So you're on the trail, you want to place your sweep angle right. Just point the sweep toward your belly button. It works really well. It gets you in the ballpark and it starts setting you up. But you know, a lot of these numbers, if you start really measuring your handlebars and stuff, oh yeah, this is a 65-degree head angle I wrote there, and yeah, with these different handlebars and stems. But the thing is, these numbers are important. And if you haven't put these values in a meaningful way into BikeCAD, you're going to end up with these weird fits. And you know how, like, I don't know anybody who's been making bikes and have been working with BikeCAD, they go, why does this bike work so differently? I expected some different results. And it's probably because you're really screwing up here. And I would say go down all your, through all the settings and get your stuff as accurate as possible so that you can have reproducible results from bike to bike. Here I talked about designing. This is a spreadsheet, and I just wanted to show this in terms of, we talk about CAD. That's great. First world's awesome. We kill it with all that stuff. But, just doing the math, having a spreadsheet, Google Docs, Open Office, all that shit has a spreadsheet. You can solve most of your problems from a frame building perspective mathematically, and all of these are driving parameters. Essentially, these are what you tell it, and these are driven parameters and some fixture settings over here. But the thing is that we start learning, especially going through that drawing process, what's a driving and what's a driven parameter. We don't want to be building around driven parameters. We want to figure out what the driving parameters are. So here, I'm trying to isolate things that I'm telling it and then things that are calculated from those original values. Now, when I'm working in a SolidWorks environment and I'm working on a bicycle design, essentially, this is an assembly. And before I've added any tube, you can see that I've got equations here where I've mathematically defined all of these relationships for the bicycle at hand. This is, some of these are, I wanted to have it early on where all my driving parameters were first listed in the list, and then it went to all the calculations. But I found that ended up being too clumsy and difficult to work with because, we're into 120 equation fields here. But having it by name and grouping them in meaningful ways started making more sense. So the driving and the driven calculations are mixed, but I can find things easier, and that's what's more important. But the thing is, I've done all that from a mathematical point of view, and before any part has been added to the assembly, I've defined these planes. Well, these are the equation values over here. But then I've defined all my planes and axes in the assembly before any parts have been added, so that I can mate my down tube right on that center line and right on that plane, and that's where it goes. And I know where my front axle is, I know where my steering axis is, and I can just start mating parts in there. And this makes it really flexible when you're dealing with different configurations. I have, like, at this point, 10 different configurations of different types of bikes or different inputs, different components, different yokes. I've gone through development of various, machined yokes to printed yokes and things like that, or non-yoked systems where in the configurations parts change and move around, and tubes get cut to different parts and different head tubes and things like that. But the thing is, it's like by having this foundation that everything's built on really makes that work out in the long run. Now, there's a huge infrastructural cost to doing this. I don't expect a novice builder to go through all this, but start thinking about it. This is, I'm trying to do experimental developmental stuff where I'm trying to figure out the answers to puzzles and things like that. So you want to think about long range, how do things all work out? But I have reasons for having to go down this road that lead me to solutions of interesting problems. And of course, a 2D print coming out of my solid modeling files, and we can see here perspectives, things that we can't see in BikeCAD. What time do we have, by the way? 7 minutes left. Okay, let's see if I can bust this out. I told you I was going to be hammering at this thing. But we can see perspectives in various other dimensions and interesting dropout configurations. Metrology. So we need to measure stuff. Any of the stuff that we do, we need to measure. We have calipers and micrometers and gauging comparison, all this sort of stuff. But one cool thing I've learned over the years is using the DRO of a milling machine as, in a way, a ghetto CMM, where you can actually set some weird thing up in your mill and then find center hole locations using the XY CMM, and you can measure something that you might not have had any other way to measure in your shop because, of course, you don't have a CMM laying around. Also, imaginary measurements, where I talked about that handlebars sweeping to your belly button, or you can only ride as fast as you can look ahead, or flat light is darkness, because we really stop learning anything once light goes flat. Those are things we gauge, but the thing is, it's like they're kind of imaginary, but they're useful, and we need to understand that stuff. Reverse engineering, just copy the work of others, start there. That's a really good way to do it, but you really want to understand what they were doing and try to understand what's happening, and reverse engineering helps guide a novice designer into understanding what might have gone into the minds of someone who might know better. 3D scanning is getting real big right now. We have several types of 3D scanning. If you haven't, most of it's LiDAR based, but we have the rad shit, CT scanning is like, oh my God. You can do a QC on a tray of 1,000 parts in like 2 seconds or something like that. It's nuts what can happen with CT, but white and blue light scanning and stuff like that. Imperial versus metric, I've discussed this at times. Imperial is a system of divisions, metric's a system of decimals. And as an example to elaborate on that, or to make a point there, it's very rare to see 3.375 millimeters. That's coming from a system of division. Just like 1.3 inches, it does happen, but it's not common. You're really not going to see it. Typically you see that because they rounded, 1.25. But the thing is, it's like these types of things are usually flopped because they're coming from different places. So if you're reverse engineering something and you're getting some weird thing, it might be because you're framing it in the wrong environment. Take photographs, learn at bike shows. I take photographs all the time. I take a photograph at a bike show. I can analyze it later. I can stare at that thing and wonder how did they do that? What were they thinking? The Sageda and the chord are trigonometric identities, and not identities, but things. I'm drawing a blank, but they're very useful in reverse engineering. I love the Sageda. And here's trigonometry. To me, this is the definition of trigonometry. If you notice, the sine isn't here and the cosine isn't here. That's impossible. They can't be there. You might find an equivalent line, but if you notice, that's the angle, that's the coangle. Why do they call it the coangle? Because it's complementary. It makes up the other half of the 90 degrees of the angle. That's why everything on this side is a cofunction, a complementary function. This side are not. That's because of where they're located. That's why cosine has to be right there. So kind of understanding trigonometry is really important. All that math you saw me do, all that crazy shit, I'm not a genius. I'm not good at math. But what I do is I use the tools that are available to me. And if you use this and you're solving some bike problems, you can create, if you know trigonometry and you talk about identities in school, you can create your own identities using this that actually create really cool mathematical shortcuts that just by using this and understanding this, where you go, oh my God, that's interesting. And also, what's the secant, Anyway, this is pretty cool. That's the definition of the Pythagorean theorem. That's a Chinese proof that came out maybe 100 years later. Very cool. Pythagorean theorem doesn't rely on squares. It's any shape scaled by the size of the triangle, which when I learned, I was like, because I'd only seen squares. It can be anything. Triangles, rectangles, Mickey Mouse heads. As long as it's scaled by the side of a triangle, it works with the Pythagorean theorem. Okay, modern production methods and common use. We've got a couple guys over there that know a lot about CNC machining. We have water jet cutting. I think it's I joke, I say it's the king of machine tools, because what water jet can do is truly unbelievable and so valuable. I think it's supplanted the lathe. There's various things you want to do when working with that. No dead stop corners, and you want to keep your table costs down. That's every time something gets plunked down, you're going to get charged. So you want to maximize what happens for each time something's put on a table. Fiber laser in terms of cutting. Same thing with table charges, but I believe you can't cut titanium with a fiber laser. Is that right? Anyway, but no dead stop corners again. You want to build in some radii in your corners, no sharp shit. CO2 laser is pretty cool. That's what the makers use when they're cutting leather or plastic in the in the maker space. It's fairly usable, but we have fiber lasers for engraving and marking. If you look at some of the machine, like Joe's Cobra fixture, he's got a fiber laser now where he's marking parts. And that's a really cool thing. If you're into making stuff and you just need shit anodized and you want to, your game is actually marking it up, well, fiber lasers are your game, and you want to like start looking into that. 3-axis CNC, really great, really cheap, you know, from a perspective. None of these you really want to waste your money on unless you need to, and it's very important that you do. Minimize your use of the ball nose. That's very expensive once you've added a ball nose in there. All the fancy profiles that you see and stuff like that, there's a heavy burden on that, and if you're starting out, try to avoid that. 5-axis CNC is coming online. I know of a lot of people that have this. It's extremely expensive, and only certain shops will have it at this point. But I will say, if you choose your parts wisely, parts that have complex are very difficult to get setups that might be multi-part setups. You might be able to get in one setup on a 5-axis that actually ends up maybe not saving you money, but you actually end up with a better part by doing a 5-axis rather than multi-setup 3-axis. So it's something to kind of weigh your options when you're looking at, like, I in the past year had some post-mount brake adapters done where in 5-axis it was a one setup part, and it did some stuff that might otherwise involve some heavy tooling costs with a 3-axis. And of course, 3D printing. So 3D printing is what everyone's talking about right now. We have DMLS, SLM, CMM, all that sort of shit. There's different types of 3D printing depending on what you're working with, what your price point is, all that sort of thing. I will say, you really want to get your modeling game together for working with 3D printing. And also, it's a very important thing to consider. It can get some people into real trouble, because usually when you're going to get something machined, you're going to go to a machinist or a shop or something like that, and they're going to give you hell if you bring them some stupid ass part that they know is going to break, and they don't even know shit about bicycles, and they're like, this is bad engineering, bro. You know, so you might get some filter there. With the 3D printing, it's like, yeah, you're going to order that part, it's going to show up, and you might put it into production, and it's terrible. So you really need to like check yourself on that stuff, because the inexperienced person can get into a lot of trouble by not filtering their stuff through some of these systems. You know, I know if I go to Mark with some part and it's bullshit, he's probably going to call me out on it. You know, that's helpful for me. I want that. Here's an example of just using some water jet cutting. I think it's great. A nice bridge. You know, I'm minimizing my use of material. It's a very strong part in a certain axis. It fits within this confine. I can make a whole bunch of them for cheap. You know, very nice use of a water jet environment. And you can do really cool things if you understand how to use it and how to use it well. This is a fiber laser marking that was used on some tooling registration. Nice type of thing. You want to be careful with precision marking because it's an optical system, not a mechanical system. With the fiber laser, it's a galvo type system, not a XY type system. So you really want to do your setup right if you're going to be using calibration marks and stuff like that. Here's just 3-axis CNC type of part. Very expensive here, where we got some rounded edges, these internal webbing and everything like that, where we have radii at the bottom. You know, there's things that you want from a mechanical engineering standpoint of this really makes it strong, but you've just doubled the cost of the part. You know, and we're always, economics are a powerful and huge force in engineering. You know, we talk a lot about materials, we talk about numbers, we talk about math and physics. Economics comes ahead of all that stuff. Money and time are huge. And this type of machining is very, very expensive. So you really want to choose your battles. You know, this is what's going on. This is just a Gerbil environment where I was machining the wheel wells for the skateboard on it was a $150 Chinese CNC machine. Terrible, terrible machine, but it got the part done. But, you know, here's just basic tool paths and G-code, you know, that kind of environment. And these are interesting things to work with. Some 3D printing, fairly raw stuff out of the shipping crate type of thing. Fitting up a Paragon hanger there with a snap ring. I've got my PVD sidewinder type brake system. Chainstay yoke, this is the part I really love. That seat stay yoke solved a lot of problems and did it in a really cool way. So this stuff's really cool. It's really getting to be available now, where it was only, for a long time 3D printing in metal was a thing, but it only existed for Boeing. It only existed if you were a defense contractor. But we're starting to get it to the point where we can really make it worth something. But we really want to maximize our value we're getting. If you can use water jet instead of 3D printing, use water jet. Definitely. Better place to go. That's great money spent, and it teaches you a lot. Working with vendors, importance of drawing. Swear to God, how many times have I done a model? I've spent all this time killing myself with my solid model, and just because I'm old school, and kids these days don't do it so much, but I'm preparing a 2D drawing to go along with my solid model to give it to my machinist guy, and I catch something totally wrong while preparing a 2D drawing that exists in my 3D, and it's like, oh my gosh, thank God I was preparing the 2D, because it kind of gets you into a whole new environment to look at your part and really say this is what's what, and you can catch a lot of problems that way. And right here, working with vendors, Mark at Paragon, he's a huge resource for people, in terms of what he does. If you can order a part from Mark, you're doing yourself a huge favor. It saves you so much money and time to rely on his expertise and economy of scale to get parts that are really good and very well priced for what you're trying to do. He provides 2D drawings and some 3D models that can help you integrate it into a 3D environment. Also, there's some integration with BikeCAD, so you know what it looks like in a 2D environment. So it's a very important resource. But also, we have other machine shops around. So if you have something special and Mark can't do it for some reason, or he works at a certain scale, you have local bros. Maybe they're starting a machine shop and they need some work. There's remote machine shops I haven't exploited much, because I think there is real value in being able to walk into the machine shop and talk to your machinist. They are a huge resource for the designer or the engineer, because they'll call your bullshit. That's what machinists are supposed to do. And they don't want to waste their day making junk parts. The mail order brides, this is with 3D printing, we're getting a lot of this stuff, and some machining. We're sending off and getting stuff in the mail, either water jet, 3D printed, machined. What happens when we work in an environment where we can't really go to the place that we're at? And I think you really have to question your abilities, your vendor's abilities, and your communication level at that point. And then one thing I do, I'm going long, but hey, we're going to run this. The debrief, I have a website where I post a lot of my stuff, but that gives me an environment where I can distill everything post-project and clean up my notebook, make notes, post models, and clean everything up. Sometimes when we're doing a big project, there's this ungodly push near the end to just get it done. And sometimes you just start slashing and burning at models and just making shit happen because you need to get it done. And that happens, that's real world. But the thing is, once you're done, the dust is settled, clean your shit up, get your drawings squared away so that they're presentable, all that stuff. Take your photographs, get some critique on your work. In the modern era, critique is like the worst thing that ever happened, and someone's going to get triggered. But the thing is that if someone doesn't talk shit about your stuff in a specific and meaningful way, how are you going to grow? You want someone to point out your errors. You want someone to say, if you had done it a different way, this way, it would have been better. And you go, son of a bitch, I'll do that next time. Thanks. You want that. You want to invite that. And you want to evaluate, we started this with, you're solving a problem. Okay, did you? If you don't do a post-mortem where you go, did I solve the problem? Was this in fact a success? For a lot of people, just building a bicycle might be a success. Once you evolve and you get to the further ends, it's like, well, did it truly solve the problem? Was it a beautiful race, like an excellent race bike? Or was it the cargo bike that fit all the needs of the person that was doing cargo shit? Like, did you in fact solve the problem? Because if you haven't evaluated that, you don't know. And how do you grow, right? Intellectual honesty, I think that's a big one. It's in the vernacular these days. Julia Galef online, if you want to look it up. But she's talking about that. I've been posting a lot of my work to the internet, and that serves me a whole lot more than it serves other people. Yeah, you guys get to read it. You get to, I share it with y'all. But the thing is, me going through that process, me getting the critique that I get from other people, me having to clean up my act and write things down, writing things down in words, not numbers, can really help you dissolve what you're trying to say or do, or explain what you're trying to do, and is really important. I think it's a valuable skill that engineers need to do, is learn how to write and do that, because it's a way of dissolving thinking and puts you in a place where you have to get it all worked out. So in development, that's basically, okay, you're engineering and you're designing stuff. Well, you've designed one. Well, now you're going to do number 2, and then you're going to do number 3. Well, if you're working on a path, you're doing development. And we want to have a step-by-step pattern. We want to have it documented over time so we know where we're going. We want to be able to predict where we're going or where we're trying to get to. You want to be critical of each step along the way. It's not a temple. It's an opportunity for you to learn and grow. And learning to write well, that's a superpower. You writing things down is one of the greatest ways of, I can't stress it enough. I barely knew how to write, I don't know, 20 years ago. And I started writing, sharing my ideas, and I've grown over time. And it's really helped my ability to think. So I talked about development. This is some stuff you saw recently on Pink Bike. Oh, there we go. So I'm talking about meaningful development and everything like that. This is on a test rider's bike who's doing development work for a major company in SRAM. And this is from the World Cup just recently. And what do I see here when I see these pictures? I see a brake adapter stacked onto a brake adapter, right? Well, everybody likes to talk a big game and how we do things in the World Cup and how much testing we've done and everything like that. These pictures are obviously 220 millimeter rotors, but they were taken a year apart. Now, certainly somebody that's working in development for a chassis manufacturer that has this on the first ride, once they got those new parts and was just trying to cobble it together to make it work, or you're at the racetrack and the shit just shows up and you're doing something, I could excuse that. But he's doing press, and he's had these parts for a while. And for some reason, this major name brand chassis manufacturer and parts supplier don't have a brake adapter. Now, that would seem to me the problem you'd be solving that week after getting the parts, but it hasn't been solved. And here, a year later, we're seeing a top racer doing exactly the same thing. So I would really question what kind of development is truly going on between those people, because this is some pretty obvious shit. And I don't think anybody that works in motorsports would allow this to happen for more than one afternoon. Development. Here's how we traditionally look at, this is rear springs for a motorcycle, CTX 700 that I'm currently riding. I was doing some spring work. We're talking about some equilibrium states for various spring rates in the system and how it affects it. This is a fairly traditional view of looking at springs in a suspension system. But in development, we talk about that. Some stuff I'm working on. I haven't done a lot with suspension recently, but thinking about, instead of displacement and equilibrium with forces in a suspension system, how about instead looking at what kind of energy is being stored in the system and how to better predict what spring rate we want based on the energy that the system needs to consume. And that's a fairly interesting way of looking at the problem. And when we have these frameworks and we can start looking at energy rather than just force and displacement, we might be able to learn something. And these are the paths you want to go down on your development track. Tooling. You want to build bikes. You need a frame fixture. I talked at length about Arctos frame fixtures earlier today. And different frame fixture environments have different values to builders depending on what your needs are. The needs of a builder that's using lugs on a fairly traditional design is very different from mine, where I'm looking for a coordinate system to build pivots from, or some very complex setups for very different parts of the bike, where I need to work with a table or a whole different fixture type and what kind of access issues we have. You know, we have accessory fixtures where we have forks. Stay fixturing is a brutal detail that a lot of builders fight with a lot. Caliper mounting, I was talking earlier about caliper systems. Well, if a system is erratic and doesn't function according to any methodology, it's very difficult to build flexible fixtures that can work with a 120 millimeter rotor or a 220 millimeter rotor if the numbers are all bouncing all over around in space when they definitely can't from a mechanical point of view, right? And then bending. This is the big one. We were talking to Rody earlier today. That guy over there, he got 4 different bending systems in his shop. You know, most builders wish they had one, you know? So he's definitely put a lot of work in this, die and follow block, press bending and mandrel bending and stuff like that. Different types of bending. And I would say sometimes you can just, you know, send your bending out of shop. You know, that's how I did my seat tubes that had a, you know, that 3-inch center line radius on a 1 3/8 tube is an insane bend that nobody without $1 million mandrel bender is going to do. But I had somebody with $1 million mandrel bender do it, you know, because I wanted to solve the problem that bad. It was really important. This is Skynet, my second fixture recently. It's pretty interesting. It's very affordable and cheap, designed for people to be able to produce very inexpensively using manual machine tools, manual mill and lathe. Someone with a high school level of capacity with those tools should be able to fabricate this, use any type of surface. Anyway, I'm just showing that I've got some modularity here. I have a whole separate head tube area, a whole separate seat tube area, chainstay area. If this were on a breadboard of any kind, I'd be able to place anything in relationship to an XY there. I just showed it without the breadboard for simplicity. Here's a calculator that's needed with that fixture. I was talking earlier about driving and driven parameters. So to set the fixture, here are the driving parameters of the bike that are required to set my fixture. And there's 17 parameters here that will end up with the fixture being set. And what I think is very interesting here, if you have, this is assuming that you might have a bent seat tube and different size front and rear wheels and tires. But if you had a straight seat tube and the same size wheels and tires, this list of 17 goes down to 9 parameters. And when we talk about refining and figuring out what are truly driving and driven parameters, when you start simplifying systems and you've dissolved it down to very simple levels, you're probably working with the real numbers. Someone might want to make an argument for top tube length with me, and I'll be like, show me how that works. How does the math work? And they're going to show me some really complex bullshit that's relying on a whole bunch of crap. And it's like, no, dude, the math's simpler with this. That's the truth. Materials, I'm not going to talk much about materials because that could fill up another whole day, but be very intentional. You know, steel is a shitty material to work with, except for all the others. We work with it. People say steel is real. That's half the sentence. The whole sentence is steel is real easy. So we work with steel. You know, were it my dream, I'd be working with aluminum and carbon fiber mixed together, but that requires a whole bunch of stuff. But titanium's a really terrible material for prototyping, is one thing I will say. Titanium is very expensive, and it's very hard to machine, and welding it and everything like that requires a considerable investment. So I would say, even if you are going to be doing some titanium building and that's your whole plan, prototype with steel, just churn that shit out. It's cheap, it's easy, you can bang it out, and then when you've got all the pimples worked out and you've got your muling and testing worked out, then go to the fancy material, work it out there, because your time and money are better spent than that. I'm not saying which material you should work with, just it's not a very good environment to be prototyping in. So this is the last slide of my lecture. I hope they haven't kicked us out yet. And so before this, I've been talking about how to think, methodologies, and all that sort of stuff. And this is when we get to the shred it. We're finally talking about bicycles. I have a lot of topics here. Maybe they're hard to read from far away. And there's a ton of them here. And relating to the bicycle, I'm open to talk or answer any questions until they come to kick us out. But I figured I'd write down various things things people might want to bring up if they want to raise their hand and ask. And I'll take your flogging also if you want. Yes?
A couple slides back, you talked about questioning like what's not working
Okay, and testing?
during the critique process that you do.
Okay.
I think it's also really important to notice what's really working well.
How do you evaluate that?
Well, what problem are you trying to solve?
Right. Okay.
Like, I mean, I'm kind of a feel guy, but like, you know, like this really feels good, and so I want to know, okay, did that happen by accident, or what makes it feel that way compared to this other thing?
Mm-hmm.
I mean, maybe it's just a different way of looking at what you were talking about too. But
Sure. I mean, I guess you're talking about when I was talking about bracketing, and I was like saying, looking for where systems break down. Well, in lots of ways, you know, it's sort of like from a metrology point of view, it's like you don't necessarily know when you're there, but you know when you've gone past. So from what's performing or feeling good, a lot of times it's just easier to find out where things are breaking down. I mean, it's like, yeah, okay, it feels good. Well, what does that mean? What does that mean it feels good? How can you quantify that? Like, I mean, I know this is engineering talk type of thing, but the thing is, it's like, okay, it feels good. How about this other thing? Have you tested all the options in that area? What parameter are you changing that is making it feel different? I talked earlier about flop being an important thing. I would say if people were looking more at flop right now than trail, they'd probably be doing themselves a service, because I think that's where you're going to start feeling real differences rather than big changes in trail, because currently I think we have significant amounts of trail on most modern off-road bikes of any sort.
Would flop be the same as caster angle, or is caster angle different?
No, I mean, I guess, you know, when we talk about caster, we're in my point of view, and I could be wrong, we're talking about that system of the wheel following behind the steering axis, and it's that contact patch and the friction created by that really starts that happening. You can imagine in a frictionless environment, that system wouldn't function. Where does the friction come from? It comes from the contact patch. And that's why change in tires and tire pressures can really affect the feel of a front end. You know, for my clunker stuff, I use 3-inch front tires, 29 by 3-inch front tires. Huge amount of contact patch, especially if they're not big and knobby and heavy. Thank you folks for coming. I appreciate it. It's nice to see you. But huge amount of contact patch, and it changes how that whole caster system functions merely because of the frictional change. And that's very important. But in terms of the angle, I think the real angle that's important up there is the head angle. That's your steering rate in a way. And largely, we're in the same range. Like, I've been doing 65-degree head angles a lot for mountain bikes, for a performance mountain bike, whether they're rigid or suspended. And I'm actually going to start steepening up my head angles because I've kind of found some pretty good areas with front center that perform very well. And I'm trying to really play with that front end and get that the flop to feel right and feel light and not so lethargic when I'm riding. A lot of that comes from my development with the all-road platform and comparing that with the clunker platform, where the clunker, in the way I did it, it's great. I mean, you can shred trail on it, but the thing is, it's like, it just has this fat, lethargic feel. I mean, obviously it's got a big 3-inch 29 front tire, but the thing is, it's like there's other things I can do. There's other parameters I can change, and one of them is the flop, and I did change that in my most recent clunker, but I think there's a way I can start steepening front ends, but I have to start. A lot of this comes with 3D printing, where I'm starting to be able to do things with my stem and handlebars that I couldn't do with bending and stuff before, where I'm gaining the space that will allow me to keep front centers where I want them and have a steeper head angle. But you know, of course, there's an aesthetic property there where you can shortcut a lot of the stuff by just flipping the stem backwards, you know. But again, do you want to be that one? You know, I spoke with Sam about that. You know, before I did my Warbird, which was the first bike I did with my fancy front end there, and I was talking to Sam at Naked Bikes, and Sam's a very smart guy, and he's trying to both make money and push his things, which is very hard to do. I'm not worried about making money, so I can try and waste my time on whatever I want, because this is a fun hobby. It's really good. I love it. But making a business out of it is a whole different game. And it's very difficult to try new different things, because generally customers aren't looking for that, all right? But the thing is, I was talking with him about front-end stuff and this way we were going before either of us had done any of our handlebars. And I was joking about who's going to be the first asshole to build a bike around a backwards stem. And it turned out, in a way, I was. But that's different, because there's a no man's land, we called it, where there's that distance in terms of given a certain front center, what you can do with a forward-facing stem and what you can do with a backwards-facing stem in terms of hand grip position. And then there's this area in between. It's the no man's land that with a traditional cockpit you can't do, either forward-facing or rearward-facing. And so what I did with most of my work was I got us into that no man's land, right? And then there's different costs and things with crossing the steering axis. And it's a cost not in handling of the bike, that doesn't have any effect, but it's in actually the fabrication when you go to put that part into the lathe and you want to go in there and face off those interfaces, because bearings need square interfaces. It's a part a lot of people skip. Like if you have a bike that works like shit on the handlebars, it's always creaking and working like shit, chances are that your frame isn't faced or your stem isn't faced. Most cast stems that you might buy in the store are going to be horrific. I mean, we're talking 10 thousandths off of square from axis. And that's not how bearings work. So when you have what we call in a headset system or a threadless system, that truly relies on every face that it mates with being square to the steering axis to a bearing quality for it to function at its best. Well, we're never going to meet that with standard machining practices, but the thing is, we can certainly come a lot closer than 10 thousandths off in deviation, and so, I typically machine all those. Anyway, I'm on a tangent there. But what I'm just saying is, there's a difficult point to cross when you're crossing that, because when in fabrication, you want to go in there and be able to face off those surfaces, and it's very difficult to hold the part and everything. So if you notice any of my system, the lug that holds the bars will be on one side or the other, kind of come tangent, but that's how so you can get in there. Any other questions there? Cool stuff. What's up?
There's a certain amount of crowdsourced failure pictures and anecdotes. I look at that a little bit. I'm not sure if that's in your
Well, failures are interesting. I mean, there's different types of failures, and also
website of busted carbon,
Sure, but what I'm saying is, like, without a context, it's very difficult to understand what the failure was. Like if you notice with those failures of the bikes that I showed there, where it's like, well, one failed well and one failed didn't. But the thing is, it's like, you could show a bike broken in half and it's like, well, it got hit by a bus. Well, all right, thanks guys, appreciate you coming by. Yeah, if a bike got hit by a bus, who cares? I mean, nothing should be expected to survive that kind of thing. And so if we don't know some of the things, I mean, yeah, you can see some mechanical connections, like there's the famous picture of the bike with the head tube ripped off, that should have been mechanically connected with brass. I'm not going to name the builder, but the thing is, it's like, that's a horrific failure. That's 100% the builder and was a bad manufacturing method, or they did something wrong and those parts mechanically separated. That's inexcusable. That's something, but the thing is, what do we learn from that? Well, we learn you should weld your shit correctly or braze it correctly. Well, we knew that, right? Or if you go to, what's his name, Leuschner or whatever, the guy in Australia that analyzes all the carbon defect stuff, where he gets into it. But, he's contextualizing it and really trying to frame how the failure worked, Sometimes I look at failures and I'm like, oh, that's interesting, but how does it help me? I was talking about that broken handlebar there. I'm going down the wormhole trying to understand carbon failure and analysis and talking to engineers. And it's like, yeah, he's showing me a bunch of splinters. Doesn't quite help me understand what went wrong here or in this situation. But then again, like I've been around this game for a while. Like when something breaks, I typically know why. You know what I mean?
Yeah.
What's up?
What do you think is the next move in mountain bike geometry?
Well, certainly solving the handlebar issue. You know, the stems and handlebars that we're using are totally antiquated. Certainly you're going to see sweeps increase, I think. I'm using a 14-degree sweep on my gravel all-road bike, which I think is very nice. I'm doing a 16 on my clunker, which it's cool. It's very relaxed and nice. I did some 9s for my performance bikes, and I think there's a place for 9, but that's bench pressing. I mean, you're really racing. For 9, I think you're going to start seeing a lot more leisure use, increased sweep. I think it's really helpful mechanically on your body. It also opens up some front center space in the design. But certainly we have huge problems right now with handlebar and stem and also the dropper type environment, because the way we're doing droppers is, you know, it's piecemeal kind of, this is how it works within the confines of the existing system. But what we're going to see is chassis built around the fact that you're going to be moving the pedestal around, the pion around. Is that right? Pion. Does that help? I mean, in terms of geometry, I mean, most builders are still like certainly 10 to 15 years back right now. In terms of anything going all road off into the dirt, it should have a dropper post. And if it's going to have a dropper post, you're certainly going to want to be seeing up to 250 drops for normal size people, or average size people, I should say. And that's significant, and you don't see a lot of that. So just that simple clearance, which isn't a handling geometry parameter, but it's just clearance of body and stuff like that. I'm trying to lower my top tube for more clearance, both front and rear of the bike, just for moving around the bike. I do a lot of riding of very technical trails that involve, you know, spatial things like that. And also I'm finding different ways of riding the bike that are possible, like I said about all-road bikes being used for very high-speed, flat or off-camber fire road corners. It's not a very technical situation, well, it is at speed, but the thing is that how we can move our mass over the bike can really change our cornering speed and stability in those environments, especially on, you know, this past summer was so slippery in Northern California, where it's like, you know, I got to do tests in very slippery environments. That changing that body position helped. It was huge. And you know, we're very limited. I think one of the crying shames in recent years has been the development of the all-road bike. In essence, they gave it to the roadies to develop, and they didn't know anything about bikes, and they just did roadie shit to it. And they developed a racing protocol that was essentially road racing in the dirt. And it's like, it's such an incredible platform in a lot of ways, I think. You know, I'm a mountain biker, so I'm used to going off trail and everything like that. But the thing is, what you can do with a very well put together bike in terms of covering a lot of ground, covering it quickly, covering it on pavement or fire road or single track, you know, it's kind of that dream do-it-all bike. And the thing is, what we've ended up with in the marketplace is largely crit bikes with fat tires. And they brake like shit, they handle like shit, and you certainly aren't going to ride rad trail fast. And it's like, I believe in underbiking. I think it's fun to ride a bike that isn't perfectly well suited. I live in Marin, and most of my riding is done on a hardtail for mountain bikes, and that's very aggressive mountain biking, but it's most fun. You know, I'm not trying to set the fastest Strava time when I go out on a ride. I'm trying to have the most fun I can have. And where I live, riding a hardtail tends to do that. But I've ridden a lot of full rigid and clunker and gravel type environments, both with drops earlier on, and I've given up entirely on drops for that environment because I just think that they're generally terrible once you hit the dirt. Drop bars are, I mean, there are arguable points, but generally it's an aerodynamic tool. And once you get into dirt, aerodynamics is generally not very important. Now, certainly in private Idaho or Kansas or something like that, yeah, they're going to be doing aerodynamic shit. But they're riding ag roads in fucking Kansas. Who gives a fuck? right? And I don't care about that. What I want to do is go for a ride after work and ride a section of road, get up the hill, whatever, and then bomb down the trail coming home or something like that. Like, think about what's the value for people in the ability to set a fast time at Kansas versus having a bike that's fairly well suited for riding pavement and single track and doing it comfortably, doing it quickly, doing it efficiently, and all that, I think is really the platform. And I think in terms of development of that platform, I think looking at the, what's the race that's enduro-based? Grinduro. I think Grinduro is a much better way of looking at what we should be doing, but it's totally ruled by the marketing department and the roadies in that you'll still see so many drop bars in those environments where it's like, you know, this one stage that might help, you know, and it's like, that's competition, of course, but the thing is, you know, racing improves the breed, but the thing is that at least with Grinduro, it's more reflective of what I think a user wants to do with their bike, is just go out for a ride, have some fun, ride the road, ride the fire road or whatever, come back on road or fire road, or take that nice single track because you're at the top of the mountain and you took the road up, because that's what I want to do, you know? It's like, I don't want to like opt for the road when I could have ridden 6 single track instead. Granted, I don't have to set a record time. I don't have to be doing it like I'm on some crazy downhill bike. But the thing is, it's like I'd much rather take single track than have to take the road because my bike sucked so much ass, you know, that kind of thing. And I think there's room for that. And also, it depends on where you live. I live in Northern California. You know, we have big old climbs and big old descents. And it's like, you know, I was speaking to some people earlier where it's like, are you trying to kick me out?
You guys can hang.
Oh yeah, you can totally do that. You don't need that. I'm happy to answer questions. I'm totally all about that until you kick us out. But I think, you know, like with mountain bikers in general, the ones that have been trying rather than just phoning it in, you know, you're really thinking about where the riding is taking place and what kind of use case it is. What are the rider's goals? Because within mountain biking, even just as separating yourself from the terrain in terms of users, you know, you have people that just want to get out to the field, get high and have a picnic. And then you have people that want to crush, you know, and it's like everything in between. And it's like, well, what's your user? And it's like, there's a different kind of bike that's really, like I could build a bike that I could set my fastest times on and I'd hate riding it. Anybody that's worked around racing knows that like there's like whether it's motorsport, motorcycles, bicycles or whatever, shit that goes fast is really uncomfortable to be in. It's not a pleasant environment. It was not built to be comfortable. It was built to go fast. And yes, there's rider fatigue issues and things like that set in with very bad setups. But the thing is that, yeah, real racing hardware is not comfy, you know? Now, that's not to say you should just phone it in with a MB aught and be done with it because that's old or wasn't for racing or whatever. It's like we have ways we can work around our parameters that can maximize the conditions that a rider's looking for. And especially for these days, we have a lot of novice, well, just in general, we have novice riders that come in. They're not super tuned into their bodies. They're not athletes. They just want to go have a good time. And that's great. I love that. And we can make bikes feel better and be safer for them. And they'd actually go faster, you know, depending on what speed they find is comfortable. We all have different processing speeds. That's what makes pro athletes different than other people, is they have a different processing speed. But the thing is, in general, a lot of these modern advancements that we're looking at with bikes makes them safer, makes them easier to ride, makes them more comfortable. And that's really cool. We can push the limits and make them uncomfortable but faster. But, you know, you making your decisions in that place is very important. And understanding what parameter changes what, or how have you played with what, especially like with mountain biking, what kind of terrain are you on? I have to climb for 2 hours to get to the top on fire road. And then I can blast down sick ass single track. You're in another part of the country, you're going to be going up and down and up and down, and it's super technical, and every climb's It's punchy climb after punchy climb after punchy climb, and something that works well in that environment is going to be different than another, versus like something we generally call the Pacific Northwest bike, which is trending right now in terms of design. It's terrible in other parts of the country, but if you live in the Pacific Northwest where all they do is climb and then go down, well, that's great. You can make a super steep seat tube that makes it really nice for climbing, and once you're going down, you're not even near the seat tube, so it doesn't matter, right? We call it a Pacific Northwest bike. But the thing is, if you live in Florida, that's going to be the most hateful experience you're ever going to have, is ride one of those bikes. But that's not what the marketing people are talking about. They're just like, sick, works in enduro, and it's like, pro athletes are different animals, and the stuff they ride and how they ride it and all that stuff, it should not be applied to normal people. And also, it's not necessarily suitable as a test parameter for what should be done in general. I work with motorcycles a lot, or I have. And for a long time, doing anything with motorcycles from a performance standpoint was taking a street bike and doing a lot of modifications to it to make it perform better, right? And then we came up with the RR, which was like the GSXR, which is essentially a race replica, where they did a lot of that hard work for you and sold you a bike like they use at the racetrack, and bicycling kind of did that too, where it's like, this is just like the racers use, this is a pro tour bike. It's like, yeah, that's great, but you're a fat 45-year-old dentist. It's like, you don't do yoga for 2 hours every day. You're not very flexible, and you certainly aren't strong or fit, and your belly's in the way. I mean, like from a fit perspective, there's a huge parameter in bike fit for fat dudes or chicks with big boobs. That has a wild effect if you're riding on drop bars, in terms of that part of the body being in the way of very aggressive, like traditional road setups where you see the seat up here and the handlebars somewhere down there. And it's like, well, yeah, I mean, if you've got a belly, that's a real problem. And if you're setting your bike up like that, you're not making it faster. It's like, yeah, it might look cool when you're not on the bike, but shit, anything's not going to look cool when you're near it. It's like, so it's just like, who's the rider? What are you trying to do? It's like, you can't say, oh, it works for racers, therefore it'll work for you. I don't know. Anything else anyone wants to talk about?